All right. Okay, so hello everyone. Thanks for joining our AI Agent Frontier seminar. I'm Minjin from Virginia Tech, and today we are very honored to host Professor Tengyu Ma from Stanford. As many of you know, his research spans theoretical machine learning from machine learning theory, deep learning to reinforcement learning, and he has also won many awards, including the Sloan Fellowship, the NSF Career Award, and also best paper awards at major conferences like COTE and NeurIPS. And on a personal note, I have been actually using his foundational works in optimization landscape in my own machine learning classes, as it really shows the insights of why deep learning works and also moves our understanding from easy to hard problems in optimization beyond simple convexity. And that brings us to the topic for today, which is a very interesting and timely topic of using large language model for mathematical reasonings. And it has huge implications, not just for mathematical reasoning and theorem proving, but also for domains where the data can be scarce, especially those valuable data used for training. And also, by the way, for many of you who have been following our seminars, you may have noticed that we have broadened the scope to AI agents, which includes the main themes of reasoning and planning, embodied intelligence, and safety and security. And this talk fits perfectly within this vision. And before we start, just a quick reminder that please mute yourself during the talk. And if you have any questions, please feel free to put in the chat. I will be monitoring the chat. And towards the end, there will be a dedicated Q&A sessions. So feel free to unmute yourself to ask the questions or comments. And without further ado, let's give Tony a warm welcome, and the floor is yours.
Thanks for the introduction. Thanks, Min, for having me here. This is it's great to be in this seminar. I think yes, indeed, agent is a very trending topic these days, and with a lot of like applications. So I think you can share. How do I see? My screen is sharing. I'm sharing the screen, right, for the slides, right?
Yes, it's crisp and
Somehow I
clear.
cannot see it. Okay, sounds great. Okay, cool. So I guess I will just jump into it. This is a work on theorem provers with large language models, and the techniques, as you see in the title, is that we are interactively conjecturing and proving, like kind of like having two players doing both conjecturing and proving. So this is a joint work with my student, my former student, Ke Fan Dong, who used to be at Stanford, and he just graduated and joined OpenAI. So okay, and I have to say that I think the talk is probably I only have like 30 slides, and probably it will just take 35 to 40 minutes. So feel free to even interact me in the middle. I guess Ming will organize the chat, or feel free to ask me many questions at the end. We do have time for any discussions. I was thinking to add whether I should add more materials in it. I thought that it's probably just better to stay focused on one thing, even though that the materials here are not that heavy. So I guess the overarching goal is to improve the reasoning capability for in some sense, most of my team is working on improving reasoning capabilities, starting from like about 2 years ago. We had a bunch of failed projects. This is probably the only paper we really published out of this effort. So and I guess the rationale is that it sounds like reasoning capability appears to be the only barrier between us and AGI. Maybe this is a controversial statement, but at least reasoning capability is one of the major barrier between us and AGI, or ASI these days, artificial superintelligence. And how do we define reasoning? I guess at this moment, I guess for both academia and probably for the broader industry community, people mostly focus on coding and math for reasoning. And part of the reason is that these are easy, kind of like a well-defined kind of scope. And also, I think there's a wide belief that if the algorithms can learn coding and math they can be extended to learn other kind of reasoning behaviors for other domains like legal reasoning, maybe reasonings in executive decisions, and so on and so forth. So and also, this coding and math are what we are familiar with, and they are well defined. So that's why I think most people are starting with this. And we focus on math. And I think I talked to many mathematicians and about using large language models to advance math, and so one of the common concerns I got from mathematicians, maybe not this audience, is that, can large language model really understand and or they are just a pattern match, right? And can they really solve Riemann hypothesis? There's any chance there, right? So I think my response to this is that, first of all, probably large language model has a better chance and a better understanding than any of the existing approach people have tried to automate mathematical theorem proving. And what people have tried are like pretty much kind of like a search-based automated theorem proving using formal language. And I think those kind of classical approach, in my opinion, really doesn't understand, right? You are just really brute forcing, or maybe a little bit better than brute forcing, right? So like you are searching somewhat brute forcefully over all the solution space. And those are really just machines, right? That are executing some mechanical way to search through the tree with some pruning, so on and so forth, without really any mathematical intuitions. Whether large language model can understand or not, that's open question, right? So we have a lot of debate, and I feel like these days the debate becomes less intense in some sense because, even though you can say a large language model are not, we don't know how large language model understands internally in the weight and biases in the activations, at least they appear to understand, right? You can ask for the reasoning trace, where you can ask for the rationales, and the large language model will give you a reasonable answer there. So so to some extent, I would argue large language model are much more similar to how humans learn and behave, and than the classical type of automatic theorem proving. So you can extract vague intuitions from few short and many examples by prompting, right? And pattern matching is not something humans don't do either, right? So I feel like many of my research on mathematical stuff are originated from some pattern matching. You say, oh, this sounds like some problems that can be solved by linear algebra, and then you try more linear algebra on it, right? And then maybe you find out that eventually you need some advanced linear algebra or something else. But at the beginning, we often do some pattern matching. And humans can have imagination and hallucination as well, right? So, and it's very hard to draw a clear line between them either, right? So many of the mathematical innovation comes from some crazy imagination. And eventually people make it, formal and correct. And now people, large language model also have like self-reflection capabilities because of the RO training with long COT, and it sounds like people are kind of like converging in believing that self-reflection is the main driver of this new wave of reasoning model, and that's how human learn as well. So and another thing that is kind of shared by large language models and humans are that they both seems to be not very good at very long and precise mechanical deductions, right? So I think it's actually very much acquired skill to be able to do very lengthy deductions correctly and efficiently by humans. And humans are still not very well in that, right? So like compared to the machines. And large language models are not very good at it as still these days in 2025, right? We had a lot of like reports of like mistaken numerical calculations 2 years ago. And I think these days they happen less often, but if you really go try and you still see numerical mistakes, if you give a spreadsheet or table to large language model and let it to sum up one of the columns, I think unless they invoke a tool, I wouldn't trust the results, right? So I've tried it myself recently as well, just summing up like a list of like a 100 numbers without invoking any tools doesn't seem to work reliably yet. So I just feel like large language models are very similar to humans, and that's one of the kind of like one of the reasons why we have some convictions in this to get into this. And even expanding on that idea, right? So if you think about it, artificial neural networks are really just very good at simulating biological neural networks so far, as we have seen, right? So and the learning process of the neural networks are not very different from the biological process, even though there's some debates there. And they both learn a lot from the experiences and data, and don't do that much of like a reasoning. I think in like 1700, right, there were a lot of debates about how human learns in the philosophy, right? So there's this rationalist and empiricist, and I think ordinary humans are learning from the experiences more than from deductions. So, and if you compare humans' capability and large language models' capability on math, and you can see probably 2024, I think we are probably at the humans' capability in 1500s, and in 2025 we are kind of like getting towards the humans' capabilities around 1700 probably. And the question is that there are still like 200 years of like mathematical advancements there that the large language models cannot capture, and how do we get there, when we can get there, so on and so forth. And I guess the main attempt is just we just keep training the networks with more data and so on and so forth, right? So and maybe one other slides about context on why we are working on formal theorem proving but not natural language theorem proving. I think the reason for that is that the formal verifiers, Lin, Isabel, so on and so forth, they can reliably test the correctness of the formal proofs, and that's very important because because of some of the reasons I listed here. So one of the benefit is that this abstracts away the ambiguity of the natural language, so that we don't have to basically we don't have to kind of understand the ambiguity that much, and also we can forget about many of the other knowledge that the large language models already have, so that you can use smaller models, right? So you can have like you can forget about any of the other natural languages, and then only focus on the formal language and focus on this particular domain. And that's why I believe that maybe a smaller model can work actually here with a pretty good performance. So 7B model seems to give pretty good performance on formal language, even with training on a few billion training tokens. But I guess even though in reality we do train on like probably 200 billion tokens, or maybe more than that. And another two objective and two reasons in the middle of the list here is that because of the objective and reliable evaluation, it's really easy to compare the results, right? You don't have to think about, if I read a paper, then whether I have really a good benchmark, or whether my benchmark got hacked at some point, because like the benchmark evaluation is really objective, and there's no way to reward hacking on your RL, because the reward is really just the evaluation results from the formal verifiers, as long as the verifiers are bug free, which is not always true. But as long as you believe that the verifiers are working, then the RLs cannot hack the reward. The only caveat is that the formal theorem provers are still weaker than the natural language provers in terms of the real capability. So if you apply the so basically what I mean here is that in terms of the pure level of difficulties, right? So the formal theorem provers probably can still prove only high school, or probably a bit higher, more difficult than high school problems. And based on my test, if you use ChatGPT, GPT-4, GPT-4 can probably prove some of the more challenging questions, at least with some chance. But that said, it doesn't really mean that if you apply GPT-4 on the formal theorem proving, it can do better than the 7B model we are training. So in some sense, for formal theorem proving, you can often claim you have state of art, even there are much bigger models out there. So basically, if you just only care about the evaluation results on formal theorem proving, then many of the papers, can claim they are very close to state of art, and basically you can, if you write a new algorithm, you can claim state of art. At least you can hope to have that, and you don't have to compare with, even you compare with GPT-4, you could be better than GPT-4 to some degree. Of course, we don't really necessarily compare with GPT-4 in this paper, but that could be possible. And just give you some sense on what are the kind of like the formal language look like. The details probably don't really matter here. It's kind of like you just write everything in a slightly different language so that there's no ambiguity, right? So, and the language are designed by mathematicians, and they try to emulate how humans write proofs. So, so in some sense, they are still pretty readable, and they are designed in a pretty reasonable way, so that they can kind of like simulate humans thinking to some degree. And they are generally a little bit shorter than natural language, which also helps with the context window. So you don't have to really use like tens of thousands of context window to solve these problems. Oftentimes, I think we found that without long COT, in this paper, we don't have long COT. This predates the long COT trend. So without long COT, the length of the proof is often sometimes around like 500 tokens, maybe like 1,000 tokens at most. In many cases, it's like even much less than that, maybe 100 tokens. So you don't really need a long context transformer to study these problems. Some prior work. First of all, what are the benchmarks? I think the common benchmarks these days are these three of this, and now there are a few more, which are kind of like being built by very, very recent papers. But the common ones are Mini-F2F, Proofnet, and PutnamBench. So these are all formal theorems benchmarks where people translate, for example, high school context theorems into Lin's and Isabelle. And Proofnet is about translating college level theorems into Lin or Isabelle. And they are some of these benchmarks don't even have solutions. They only have the translations of the theorems. And because the solutions anyway are not very useful for benchmarking, because the large language model solution or proofs wouldn't be very different, wouldn't be the same as the Go solutions if they exist. So in some sense, you only need the correct theorems. So basically here, the reason why these are called benchmarks are really because you know for sure the translation to Lin and Isabelle are correct. It's not like the benchmarks have proofs. It's because many of the other data sets, as you see, don't necessarily even guarantee that the theorems in it are correct, are correctly translated or correctly stated even. So, and here you don't need the proofs, as I said, is that once the large language model generate proof, you can just use the Lin verifiers to verify, and you know whether it's right or wrong. And some of the models and methods before our paper, there's a family of like kind of like works that are trying to specialize to formal theorems. For example, there's this theorem llama, which kind of like fine-tune the large language models on formal theorem proving. There's a DeepSeek Prover 1.5, 1 and 1.5, and now there's a DeepSeek Prover 2.5. I forgot to cite that. Recently, this was released probably a few weeks ago, and there was Alpha Proof, which was by Google. And Alpha Proof is a slightly different beast because it uses a lot of compute, especially at test time. I think they claim they can prove a few questions, during the for the IMO questions in last year, and I think the compute spent for those kind of like proofs are kind of enormous, in the sense that I think they probably spend an entire few days of like a GPUs from Google for a few days to do those kind of a few questions, because the search are very heavy there. And there's also kind of small scale, kind of like smaller scale, kind of like academic papers, which uses tree search based methods, where you kind of like do a lot of search, but also use large language models to propose what you should try. but you do kind of like some kind of like tree-based search heavily. We'll discuss some of these works a little bit more in the evaluation part of the talk. So, and the training data sets, I think, yeah, I my slides is a little bit out of date. There is one more, but before our paper, there was this proof libraries, which are human written formal proofs for important lemmas and theorems. So these are only for like a very elegant foundational lemmas and theorems. And there is a data set called Lean Workbook, which is translated by large language models from natural language, high school context level theorems in Lean. And now there's a new one called Godot, a data set that was released by Princeton folks when they studied these problems. So they built a even bigger data set with somewhat, I would say, similar approach like as the Lean Workbook, but much more sophisticated and with much more cleaning. So it's still translated kind of like a data sets. So one of the differentiation between these two type of data sets is that the Lean Workbook has a very high degree of mistaken theorems. So we estimate at least, I think, okay, now I'm blanking on it. I think it's like about 50% of the theorems are actually wrong in the data set. So in that sense, like you see why the numbers that we have on the success rate of these data sets are not very high. And the reason is just because there are so many theorems that are mistakenly translated. We did this kind of like manually, like we just sample like 30 theorems, and we found a lot of them are incorrect. And some of them are incorrect, not by a little bit, it's by a lot. Yeah. So anyways, so we still use the Lean Workbook as training, and we evaluate on the performance there. So but that's okay, because we are not it's not like the labels are wrong, because when you claim you solve 30% of the problems in Lean Workbook, you really know that 30% is literally correct, and you know that the proofs are correct because the formal theorem the verifiers actually verify that. Okay, so and what are the okay, now let's get into the more details about the methods. Maybe just one more comment on the background. So like I do believe that we have a problem with lack of data. And why there's such a problem, even for RL, at the first sight, sometimes, people say, oh, RL is supposed to self-improve forever, right? So but the problem is that you need to give the theorem statements to RL, and then let RLs to self-improve. But the theorem statements are fixed and given. So so basically, at least the current RL algorithms like this, right? You just give a statement, you generate a bunch of proofs, and then you verify the proof, and you say the correct ones are rewarded 1 and the incorrect ones are rewarded 0. Maybe you have some other rewards like about the length of the proof, so on and so forth, and then you train the large language model on this a new data set where you have the rewards, right? So it's kind of like basically another SFT with the correct statements, the correct proofs. But in some sense, RL is pretty much just the same as you select those trajectories where the proofs are correct, and then you do another SFT on top of that. So, and you keep doing this. And so basically the first order issue is that this only works for the given statements, but you cannot really extrapolate to other statements, right? For example, if all the statements are Lean Workbook statements, then those are kind of high school context level statements, and it's unclear, or it's very unlikely, in my opinion, to keep training this forever, and then you can get to the college level math, because you have never seen any college math theorem statements. So and so that's what I mean by I don't really believe that we have enough advanced. And another thing is that the number of advanced theorem statements are very little, right? So you have a lot of college context statements, but you don't have enough kind of like advanced theorem statements, and we don't have enough papers in some sense. Even you just compute the total of papers that the human history, in the entire human history, you can get all of them, right? Still the number of tokens there is probably on the order of like hundreds of billions of tokens at most. I think I did a calculation. I think it's less than maybe 100 billion tokens for sure. So think about it, right? So the entire internet is only like probably 30 trillion tokens, and how many of them are papers? And with all of this, it's probably still not enough theorem statements to generalize to open math questions. So and you cannot go beyond the difficulty level of the existing data sets, which is a pragmatic issue as well. So and another technical issue with this RL and here I'm specifically talking about expert iteration, which is a simpler form of RL, where you just assign 0 and 1 reward and you do basically basic RL policy gradient. But this actually applies to generally any RL. So basically the problem is that the reward is fundamentally sparse because you have very small number of proofs that can be correct, especially as you progress in the training. Very soon you just exhaust all the simple statements, and then all the statements are left are things you don't know how to prove. And even the large language model tried many times, still you don't really know how to prove them in some sense. So and basically after a while, like you usually cannot prove a lot more new statements. And this paper by Wu et al. Measured that about 98% of the compute are wasted on unsuccessful proving attempts. Of course, whether it's a wasted is the debatable word, but at least we know that like out of like 50% of out of 50 trials, you get one successful proof. And I think it's actually the real thing in our experiment is even more severe than that. If you train for longer, actually you spend probably 99.9% of the compute on unsuccessful proof attempts. And I think the plot here is trying to show that how long time you spend on the compute to kind of like on successful proofs, right? So and you can see that like there's a long tail in the sense that there are you basically spend a lot of compute on just a very few number of proofs to try to kind of like yeah, I think this figure is a little bit harder to read anyway, but the point is just that you spend really most of your compute on just only 100 proofs after you train for a while. So, and this brings me back to, so basically this is what we initially see in the beginning of the project. I think we spent probably like a few months on this and just and we got stuck. We just found that the reinforcement learning just plateaus after some point. I guess I'll show some plots in a moment. So and this doesn't work after you train for long. So and then I start to reflect why why human mathematicians can keep going doing better and better. It's not like human mathematicians in the history, right? So now human mathematicians have a lot of understanding, right? But 300 years ago, it's not like human mathematicians have more data than large language models today, right? So like 300 years ago, there were limited papers. You don't read that many papers from other people anyways, because there was no internet. And it's not like human mathematicians have more calculators, all right? They still use papers and pens to do the calculation. And how do they learn, right? How do the human mathematicians learn from the data? So I think the difference is that human mathematicians don't seem to just do trial and error in silo. They do a lot of trial and error, I believe, but they do actually have some kind of like other type of like ways to train themselves, not just keep trying and trying, right? So, and that's kind of like overarching thing that I was thinking to do, right? So how do you simulate mathematicians development process with a little bit more fidelity, right? So, and one of the things that we found is that the mathematicians actually practice a lot on existing variants or extensions of known theorems, right? You don't just go after Riemann hypothesis, just trying it for like 20 years, lock yourself in a room and trying it for 20 years with all the trials and errors, right? So you do try to decompose the problem and find variants and find extensions of existing ones and practice yourself a little bit. And also you propose and try to prove new conjectures that are probably easier than Riemann hypothesis, and people kind of like actually interact in some sense. So that's the first step we're taking to kind of like try to be more like human mathematicians, and by introducing this conjecturing process, so which also solves the lack of data problem, because if you conjecture, then you can get more and more data. And I think that's actually, I believe that that's how human mathematicians solve the lack of data problem, because you just create more data yourself, right? The real data out there here today in 2025 are actually human generated data 200 years ago, probably, right? So the real data are actually synthetic data generated by humans in some sense, right? So for humans, they are synthetic data because they human generate the data themselves. So that's the kind of the way we are trying to solve the lack of data issue. You just keep generating more and more conjectures, and you keep generating more and more proofs, and you filter those good conjectures and proofs iteratively. There will be a conjecturer and prover, and they interact with each other. So in some sense, the conjecturer is generating a curriculum, right? So you give you generate easier questions first and then harder questions later, ideally, and you generate more and more diverse questions, and then the provers tries to prove it, and the provers will give feedback to the conjecturers as well, right? So if the provers never prove any conjectures, then you would say the conjecturers didn't do a great job, right? All the conjectures are not approachable, and the provers can give other sort of like feedbacks to the conjecturers as well. So you're going to keep training a conjecturer to generate high quality conjectures. And I think just one clarification for terminology is that we from now on, we're going to say conjectures are generated by the large language models, and statements are those data sets, those theorems or statements that are given in existing data sets like Lean workbook, just to distinguish these two types of like statements, even though they are both theorem statements. Let's give some kind of like and maybe and another thing is that there's one small detail here about how do we generate conjectures. The way we do it is that we say we are given a new statement, existing statement, in the data set X, and then we generate extension and call it conjecture Y. And the reason that we do this is that if you just generate conjectures out of the blue, it's very hard to make it relevant, and sometimes the large language model just all go off the road and keep generating more and more complex linear algebraic conjectures, which has nothing to do with some of the other things like geometry, topology, so on and so forth. So that's why we give the large language model some guide on some initial C statement X, and then we let it to kind of do an extension, which could be just a variance or could be something more complex or more challenging. This also kind of like seems to be reasonably consistent with how humans are generating conjectures. It's not like you always generate without having any prior knowledge, right? So that's the I guess I'm doing pretty slowly. Anyway, so to give you some kind of like ideas, for example, if the C statement is sort of simple equations with 1 plus x squared is less than 1 plus x parenthesis squared, then sometimes the general conjectures will make it a little more complex and compose it with some other things. And sometimes the general conjectures are trying to, in example 2, kind of like abstractify the seed theorems to introduce a variable and then make the statement a little bit more interesting or more abstract in some sense. So and this is the diagram to show how we do this with more fidelity. So and you can see that in step 1 is the generating conjecturing step where you generate conjectures from a C statement and a proof, and then you try to prove them by sampling from large language model, and then you verify the proofs, and then you give the rewards to the prover by the same thing as before. And then the real question is really just how do you give rewards to the conjecturer, right? How do you say which conjecturer are good and which conjectures are bad, and how do you use that to reinforce the correct behaviors for the conjecturer so that next time the conjecturer will generate higher quality conjectures? So what we do is we generate oh, by the way, for the proofs, so what we do is that we kind of like generate proofs, 32 proofs per statement conjectures, and no tree search, and we use kind of like a natural language proof with a reward model. So so the conjecture data sets, what we do is the following. Sorry, I was kind of like reading the slides just to fill in some details about step 2. But now let's go back to step 4, where we generate the conjectures. We generate data sets for the conjecture. And the way we do it is that we just filter from what we have generated, right? So you want to filter out the elegant, approachable, and challenging conjectures. So, and how do we do that? So there's some elegancy filter, which I'm going to discuss in a moment. And also we say, if you prove the conjecture, if the conjectures are proved 1 to 8 times out of 32 times, that means that is approachable, but still challenging, right? If it's proved 32 times out of 32 samples, then that's too trivial. If it's proved 0 time out of 32 times, then it could be challenging, but it may be even incorrect, right? So if the conjectures can be incorrect, right? So if we have no evidence that the conjectures are correct, then we don't use them to reinforce, right? So if you prove it 1 time out of 32 times, it's kind of the right thing, right? It's correct, but it's still approachable and it's still challenging. And then we can use that to reinforce the conjecturers. So how to some of the more details, I guess I probably have to skip some of the details given the time. So I think the key kind of like goes to filter the conjecture data set is that you want to maintain some diversity and relevancy. So we also apply some additional filters to further deal with that. So one of the issue is that, for example, you can collapse to seemingly linear algebraic problems. So if you give a series theorem statement which is about number theory here, right? Sometimes the general conjectures are still seems to be about number theory, but actually they are really linear algebraic problems, or kind of like a numerical problems like equations or inequalities, which has nothing to do with p is a prime. It's really just saying like p is larger than 2 implies p is larger than p squared is larger than 4. So you lose the diversity after iterative training, and that's one of the things we constantly have to fight. And what we do is that we use a bunch of filters. So one of the things we say, we have to have some relevancy requirements between the C statement and the lemma you generate. And the approach is that we insist that the C statement and the conjecturer has the conjectures use both the same lemma, right? So that so basically C statement and the conjecture should have used one shared lemma so that they are related. This is just a hack, we don't really like that much, so that's why I'm just reporting what we have done, and we are trying to kind of improve upon it and see what's the best way to do this more kind of like more in a principal way. And another idea is that we try to preserve the diversity of the conjectures by doing some kind of like a reweighting of the generated conjectures. I'm going to be very lightweight on this because it's kind of like a hack, and we try to somehow minimize the vastness and distance between the generated conjecture size with the existing lean workbook. So basically, if you see two little number theory statements in the conjecture set, you have to reweight it so that you can reinforce the behavior over time. So, but maybe let me skip some of the details here, which is not super important because we don't really think these are fundamental approach. But the principle I think is right. The details are not necessarily the best way in the long run. And also we have this elegancy score where we try to kind of filter out those kind of like very very kind of like non-elegant statements, which could be something like you have a very long statement which is compose multiple simple things in a messy way, and the solution is very simple. So you could, for example, have a like a almost trivial statement that are stated very lengthy way, which is not really what we are looking for. So basically we have this very trivial elegancy score, which is like you try to say the proof of the statement should be long and the length of the conjecture should be short. And of course, we don't want to encourage long proof either. But in a prover, you try to encourage short proofs because you have a discount factors in the RL training. So in some sense, you encourage both the short proof by the prover and also encourage the short conjecture length by the conjecturer. Yeah, we just remove the conjecture to the lowest 20% elegancy score. And there are some more details on how to implement this, but I think I will skip some of those. These are in the paper, and there are even more descriptions in the paper. So just going into the experiments, so we try this on the Lean workbook, which has 89K high school level formal theorem statements. And here we are showing the cumulative pass rate, which is the percent of statements we proved at least once during the training process. This is a set that doesn't have any proofs. We actually release all the proofs we can we were able to prove so that people can reuse them. So the baseline is just RL, we call it expert iteration in the paper. Which is basically like just a 0-1 reward with kind of like iterative, like a between like a sampling and retraining. And parallel sampling just means you don't do any training, you just keep sample more and more proofs. And you can see that if you just keep sampling, you're gonna prove more and more statements still gradually if you try for a long time, but the scaling is not as good. So the STP can train much faster and get to a higher accuracy much more quickly. We also try both the Lean and Isabel, and it turns out that in Lean the accuracy is much higher, so that's why we'll use Lean in the future as well. So we get basically we almost double the best accuracy. In the previous report, the best accuracy was 13%, and now we can get to 26% already. And we also try these experiments on the right-hand side where we actually can start from different checkpoints. So if you start with any checkpoints, you try expert iteration and sampling, you see that we are beating both of them. And that's very important because some of the algorithms after a certain point is actually improving only because it's just doing more sampling. The retraining doesn't really help. The only thing that the policy gradient doesn't really help. The only thing that helps is the sampling. You just keep sampling, you get more and more statement proved. But of course, then the scaling would have been great. So that's why we are focusing on the scaling effect here. And we also have tried this on Mini F2F, and some of the other benchmarks are Proofnet and PutnamBench. So and I think we get still far on all of them. So based on a similar budget of kind of test time compute. And I think even with more budget is the best. So Yeah, so and this is a bigger table which compares with some of the other kind of like approach. So I think so some of the approach in the second half of the table are using very extensive search-based methods, and you can see that their sampling budget from the large language model is much bigger than those on the top. So if you just do a rough calculation, so this intern LLM 2.5 step prover, they are using like 4.9 million kind of like sampling steps. But for STP, you know, even for the most extreme cases, you only use like 250K steps, but actually you can get pretty good performance even with like a 32K steps of sampling budget. And we try to compare with different type of sampling budget, and we see we are better than all the other prior works, you know, on each of the sampling budget. So I think just some quick kind of like a analysis on just to give you some sense on what kind of like conjectures and proofs, you know. So so these are some examples. I think I've shown the first example already, and the second example is more like the C statements, kind of like, you know, is n-1 can divide n to the k-1, and then you kind of like change the statement format in some way to say like a x to the power n-1 is modulo x minus n is less than 1, which is fundamentally very similar. It's just really a variant. And the third example is more or less just a kind of like a small abstraction of the data set. But basically, this is the level we are operating on. It's not very difficult yet. And we also found that the generate conjectures are generally having longer proofs, so which is a sign that they have they are harder to prove. So so if you measure the average length of the conjectures, the average length of the proofs of the conjectures, they are higher than the average length of the proofs in the data set, or for the theorem statements. And here's the example on what are some of the conjectures we can conjecture. So yeah, they are reasonably sophisticated, we can see, right? So, and they know, you know how to, and the proofs are longer than the C statement. Yeah, so yeah. Okay, and here are some of the statements we have proved in Lin workbook. And you can have a rough sense on the level of difficulty here. I think the question is actually not that, like, it takes like a few minutes for me to solve any of these questions, maybe like more than a few minutes sometimes. And some ablations, you know, so the our conjectures are much more approachable thanks to our reward design. So you have much more higher success rate for proving the conjectures than proving the remaining statements in the Lin workbook. So basically, very soon in our training, there are very few statements that can have high pass rate in the unproved statements. So basically, if you look over all the unproved statements, you feel like and you do a histogram on the pass rate of those statements, you found that you have like 10 to the 5 number of statements, you know, with 0 pass rate, and the very few number of them. This is by the way, this is log scale in the y-axis. So there's a stark differences here. So most of the statements have very low pass rate. But for the conjectures, you know, you have a relatively uniform pass rate in some sense. So that's how we can make progress on the conjectures. Okay, I guess these are everything. And just briefly mention some of the future works. I think one of them is how do we do it for natural language provers, especially with a reasonable compute constraint. The prover, I think on the prover side, I think there are many research on how to use the error message before, but not kind of like in this kind of context. So the Lin verifier give you error message. If you can use that, then maybe you can have better prover. And also use how to use long chain of thought to improve the prover. I think now actually with the DeepSeek Prover 2.5, they are already long chain of thought, and we can try to improve that. And in the long term, I think maybe one question is how does the formal theorem proving capability generalize to other tasks, coding tasks, natural language proving tasks, or even like more broader tasks like legal reasoning tasks. Yeah, I think that's everything. Thanks for listening. Happy to answer any questions.
Yeah, thank you, Tengyu, for this wonderful talk. Really timely and insightful on this very important problems of theorem proving. So I think we have a few minutes for a couple of questions. So let's open up the floor for Q&A. Please use the chat box or unmute yourself to ask your questions.
Yeah, I have a question. So thanks for a great talk, Tengyu. So as you mentioned, when we use reinforcement learning to train the provers, that could waste a lot of time. So do you have any comments about how to improve the training efficiency regarding to improve the provers capabilities?
Yeah, so I don't know, I think we are trying to find out some of the new methods, but not very successfully yet. But the problem is really just like what I said, very quickly, not very quickly, you train it for like probably, depending on how many machines you have, right? So, so like you train it for like probably maybe 20, 30 iterations. Of course, the iterations doesn't really matter that much here because it also depends on how you define iterations. But anyway, just training for a while, then you cannot prove any new statements anymore, and there's no reward, and you are not making progress, and it just plateaus there. So yeah, but I think one of the reason why we are working on this paper is that we thought that maybe this is not a prover's fault, just because it's probably the statements, the problem with the statements. That's why we try to generate new statements. But I think there are still things we can do on the prover side. I think using long COT definitely will help.
Okay.
So that you have more success rate for more challenging questions. I think probably looking into why the long COT is not perfect yet would be useful source, right? Like we have been playing with DeepSeek Prover 2.5 and try to see what's their limitation, so on and so forth.
Okay, I do think the training data diversity could be more helpful for that to improve training efficiency.
Yeah, so I think diversity is useful, but I don't think diversity. I wouldn't probably rank it as the #1 concern. I would say, because right now the lean workbook has a diverse set of data, and the Godel data set has even more diverse set of statements. So I think if your goal is to just do better than the current level, I don't feel diversity is a big issue yet. But at some point it will be a big issue.
Yeah, thanks. So we have a worker, but we have some findings that diversity could significantly improve the training features in large language models, and we have a theoretical analysis and empirical studies. Yeah. Okay.
Okay,
Thanks.
gotcha. Yeah.
Hi, thanks for the great talk. So this is Roshi. I also work a lot on data selection. I have one question about your talk. You mentioned you have some filters of generated conjectures in terms of diversity and relevancy, but these two metrics are usually, have conflicting goals. So if you emphasize too much on relevancy, it may reduce diversity. So I wonder, how do you guys balance these two metrics in your data filtering?
Yeah, so we have a diversity reweighting. I think the details is a little bit complicated. I just don't feel like it's the right way, so that's why I didn't talk too much about it. But that seems to be sufficient for for this work. But the reason why we didn't like it is that if you keep training and training, at some point you still got into this diversity issue, and is that a problem? I think that's the kind of the problem. But you know, it's kind of hard to say exactly what's the issue, like for going to the next level.
Did you guys do some ablation studies on, you know, this different rating between diversity and relevancy and see how they kind of
No, we just compare with nothing. Like you know, we have our method versus no such components. Yeah.
Got it. Yeah, another question is that at the beginning you motivate this work by the goal of solving some challenging mathematical problems. And the intuition is that if we iteratively generate kind of synthesize some adjacent data, maybe we gradually move towards those difficult problems. I wonder, like, if in your paper you have done some control studies and you know, do some kind of during the training, you start with some kind of relatively simple problems. Through this process, you at the end we targeted data on some more challenging problems.
Yeah. I think this is also relates to the question in the chat. So whether this can get to more challenging questions. So maybe let me just repeat the question in the chat as well. So the chat was that is saying that the conjectures are a variation of existing mathematical structures, and can this approach truly make the true novel conceptual leap required for problems like P versus NP or Riemann hypothesis? Of course, you know, I cannot really say for sure, right? Because, you know, we don't know. But I think my response to that is the following, right? So even though you look at even though the conjectures are variants of the existing statements, we do have more and more sophisticated conjectures throughout the training process, right? So like on day one, the conjectures are much kind of like simpler, and as we prove more and more statements, we give more and more harder statements to the conjecturer, and the conjectures are generating variants of harder statements. So yeah, so it's true that you are generating mostly variants or extensions, but you are gradually building up, right? So like you are generating extensions of the elementary school questions at the beginning, and then you gradually prove some kind of like middle school questions, and then you generate more and more variants of the middle school questions, and you start to prove some of the high school questions, and you generate more and more variants there. So it's kind of like you build up it's an incremental, like you it's kind of like if each time you can go 0.01 level up, right? So then gradually you're gonna keep going up. That, at least that's my hope, and that's what we have seen in the existing training run as well, which is going back to Rossi's question. So so in some sense, the success rate improving. We are, you know, the fact that we are having higher and higher success rate is the indicator that we are proving more and more difficult theorems, right? So how do you evaluate the theorems, the statement, how do you evaluate the level of the statements? It's kind of like you are, if you cannot prove it on day one, then that's a mid-level question, and you can prove it on after training, you know, a lot of questions, then on those are harder questions, right? So basically the fact that we are improving the accuracy is suggesting that we are proving more and more difficult statements.
Thanks.
Yeah, and we have eyeballed the results. Of course, we have seen that as well. Yeah.
Okay, great. Yeah, thanks for this great discussions. And it looks like that's all the time we have for question answering. Let's give Professor Ma another round of virtual applause for the truly fantastic talk. And thank you, Tengyu, for sharing your time with us and your research. And thank you everyone for the engagement. We hope to see you in our next seminar, and hope you all have a great rest of your day and a wonderful weekend.
Thanks everyone.
Thank you.
Thank you.